Jnanam paramam dheyam. Knowledge is supreme.
So, let us quickly summarize what are the steps that is involved in actually finding the E curve. So, steps to find E curve, the first step is basically to inject a tracer. So, inject a pulse tracer and then collect data. And the way to and then by collecting data, one would actually get a table of time versus C of t. So, at different times one can actually find out what is the concentration of the tracer in the effluent. Now, once this data is available, then one needs to find out this integral C of t dt by using appropriate numerical integration scheme. By using appropriate numerical integration, one can actually find out what is this integral between 0 to infinity C t dt, which is basically the area under the C curve, and the last step is to find out the E of t, which is C t divided by integral 0 to infinity C t times dt. So, that is the area under the curve. So, these are the three steps that has to be followed in order to find the E curve. So, now if we know the E curve, we know the RTD function, and we estimated the E curve using the concentration of the tracer at the output. Now, the input that was given in order to estimate such an C curve is basically a pulse input. Now, the question is there a connection between the input concentration profile and the output concentration profile? So, the answer is yes, there is. So, our tracer concentrations related. Are they related? So, suppose if I call T is my tracer, suppose T is the tracer that is actually fed into the reactor, and now if the input to the reactor is basically given by this function, suppose this is the input concentration to the reactor, that is the input concentration profile, and after going through the reactor, the tracer is actually measured in the effluent stream, and let us say if the concentration of the tracer in the effluent is given by this curve here. So, that is C out. So, that is the in, and that is the concentration of the tracer in the outlet stream or the effluent stream. So, now suppose if I place them in the same graph. So, the objective is to find out what is the connection between this concentration profile and this concentration profile. So, suppose if I place them in the same graph, and that is my input stream, and suppose the corresponding output stream is this. Now, I can write a material balance to find out the relationship between the concentration of the species that is actually coming out of the reactor at a certain time, and how is that connected to the concentration of the tracer at the inlet. So, suppose I take a specific rectangle, specific element at a certain time t, and let us assume that the fluid element which is present in the small box, and similarly if I take a small element here which is essentially at t minus. So, it is exactly the fluid stream that is entering the reactor at t prime time smaller than the time t at which I am monitoring the concentration of the species in the outlet stream. So, now I can write a material balance on the tracer. Essentially, t, which is the tracer, which is leaves at time t, that should be equal to which is basically the one in the rectangle B. Suppose if I call this as rectangle B and this as rectangle A, and the amount of tracer that leaves at time t should be equal to all tracer t entering t prime seconds before t, and they stay exactly for t prime seconds in the reactor and reside for t prime. So, basically the amount of tracer that leaves at this time should be equal to all tracer that has actually entered t prime time before this time t, and they have resided for that span of time t prime. So, that is the material balance which connects the amount of tracer that actually leaves the reactor and the amount of tracer that actually enters the reactor at a certain time t. So, now this can actually be rewritten as, so the amount of tracer that is leaving at t, that is basically rectangle B, that should be equal to sum over all rectangles A, that is all rectangles in the feed stream, multiply sum over all rectangles in feed stream, that is sum of the amount of tracer in each rectangle multiplied by the fraction of tracer in the rectangle A that stays for, that resides for t prime. So, the amount of tracer that actually enters the reactor at a time t prime before the time t, which is basically the time at which the certain tracer species is actually leaving the reactor, and I am attempting to connect that to the amount of material that has actually come into the reactor. And so, that should be equal to sum over all rectangles, that is the amount of tracer that is present in each of the rectangle multiplied by the fraction of tracer in that particular rectangle that resides for the t prime seconds in the vessel. So, now if I plug in the corresponding quantities, so if I write this expression in terms of the integral, it will be the concentration of the species in the outlet stream, that should be equal to 0 to t, that is the total amount of time that I am monitoring, multiplied by the concentration of the species in that rectangle. So, this corresponds to the concentration of the tracer in each rectangle, which is actually injected exactly t prime time before the time at which the concentration of this particular species is being monitored, multiplied by the fraction of the species that actually spends t prime time inside the vessel. So, that is the relationship between the concentration of the tracer that is actually fed into the vessel and the concentration of the tracer that actually leaves the vessel at any time t. So, this kind of an integral is what is called as the convolution integral. So, this relationship between the input and the output concentration is actually very useful to find out various aspects of the reactor using the RTD function. So, next let us look at the input case. So, let us look at the step input case. In the case of pulse input, we actually found out the E curve. In a similar fashion, here we are going to define a curve called F curve, which is actually called the cumulative distribution function. So, now in a step input case, what is done is, suppose you take a single input single output vessel, and then at some time t equal to 0. So, suddenly you provide a certain concentration of the tracer as a feed, you inject a certain concentration of the tracer into the feed, and then the concentration of the tracer is actually maintained. So, basically it is a step function, and let us say that this concentration is some C naught. So, this is the inlet concentration of the tracer into the feed stream as a function of time. So, now C in mathematical representation of that will be C in as a function of time will be 0 if t is less than 0, and that should be equal to some constant C naught if t is greater than or equal to 0. So, we assume that we assume that we are able to provide a constant concentration of the tracer into the reactor. We assume that we are able to feed a constant concentration of the tracer into the feed stream, and till what time do we have to maintain it constant? So, we have to maintain it constant. We have to maintain it constant till the effluent stream tracer concentration is equal to C naught. So, we maintain the concentration of the tracer in the feed at some constant value T naught until the effluent stream, the tracer concentration in the effluent stream is exactly equal to or almost equal to the concentration of the feed concentration of the tracer which is actually maintained in the feed stream. So, now once this is done, then we can actually measure the amount of while doing this we can actually measure the concentration of the tracer in the effluent stream. So, soon after the step input is given. So, the first step is to give a step input, let us say at some concentration C naught, and then the second step is to measure the concentration of the tracer as a function of time in the effluent. So, that is the second step in the step input experimental method. And then if we look at the schematic of the outlet concentration of the tracer, it will essentially look something like this, where as a function of time the concentration of the tracer is now going to slowly increase from 0. The time when the input is actually provided, time when the step input is provided, there is no tracer that is present in the effluent stream. So, therefore, at time t equal to 0, it will start at 0 concentration, and then the tracer is now going to slowly move through the reactor, and then it is now going to appear in the effluent stream. And so, once the concentration is measured, the concentration slowly increases till it approximately reaches the concentration, the constant concentration with which the tracer is actually being maintained at the input or the feed stream to the reactor. So, till it reaches that concentration, one has to measure the concentration of the tracer in the effluent stream. Once it reaches that concentration, then the step input can actually be stopped and the experiment is done. So, now once we measure this concentration versus time data, what can we do with this? So, we know from the convolution integral, from the convolution formula, that the concentration of the tracer in the output is actually related to the input concentration as 0 to t C in into t minus t prime multiplied by E of t prime into d t prime, where this is the input concentration of the stream in the concentration of the tracer in the feed stream, and E of t is the fraction of the material that actually spends exactly t prime amount of time inside the reactor. That is, the residence time of that fraction of element is basically t prime. So, from here, because C in because it is a step input and the concentration of the tracer in the feed is actually maintained constant at C naught. So, this is basically equal to C naught, and that is a constant, and therefore, the C out will be C naught into integral 0 to t E of t prime into dt prime, or C out by C naught, that is equal to integral 0 to t E of t prime into dt prime. So, this integral over the E curve or the RTD function is what is called as the cumulative distribution function f of t. So, f of t is essentially the concentration of the tracer in the output divided by the total amount divided by the concentration of the tracer which is actually maintained in the feed stream, and this is for the step input method. So, therefore, E of t can easily be shown that that is equal to d first differential of f with respect to time, or that is equal to d by dt of C of t divided by C naught. So, f basically says what is the fraction of that fluid which is actually leaving the reactor with a certain time at a with a certain residence time. So, what are the advantages of the step input method? The advantages are that so it is easier to perform, it is easier to perform this experiment because it can actually the experiment involves maintaining a certain concentration of the tracer at a certain level. One may not be able to maintain exactly at that level, but it is much better than giving a pulse input, because the pulse input a certain fixed quantity of the tracer has to be fed in a very short time period. So, therefore, it is easier to perform the experiment, although it may be difficult to maintain a certain fixed concentration C naught, and that is because of certain experimental limitations. And also an important advantage with this method is that the total amount of tracer, that information is not required. So, remember that in the pulse input case, in order to find the total amount of tracer, one needs to actually integrate the concentration or the C curve, and if there is a long tail, then there are inaccuracies that may creep into this integral, that is the total amount of tracer. So, such kind of integration is not required for the step input method. However, in order to find the E curve, one needs to actually differentiate the data. So, differentiate the data, and that may actually lead to some errors. So, some errors may creep in while actually differentiating this the data differentiating the concentration of the tracer as a function of time in the effluent stream. Now, another major drawback of this particular method is that because one has to maintain a step input, the step input will require a large quantity of tracers, and if the tracer is actually an expensive material, it is not a very economical method to actually conduct an experiment to measure the RTD function. So, are there other techniques or other tracer techniques to measure the RTD function? The answer is of course yes. So, other techniques are there are other tracer techniques, but these are not very commonly used because it is difficult to perform these experiments. So, one is the negative step tracer, where the concentration of some tracer is now suddenly it is actually decreased, and it is not very easy to perform such an experiment. Basically, there is an illusion or dilution of the tracer in the feed stream. And then another method which is used is called the frequency response method. It is called the frequency response method, and the third method is basically one can use inputs which are than pulse or step method. So, there can be other types of inputs that can actually be provided, and these are not very common methods, and so it will not be discussed in this course. So, next, after finding the RTD, one needs to know what are the characteristics of this RTD function, because we are interested in finding the non-ideal behavior of the reactor, and we said that the RTD function somehow it captures some information about the non-ideal behavior of the reactor. So, we can now estimate what are the characteristics So, the characteristics of RTD function perhaps may provide some clue about the characteristics of the nonlinear behavior of the reactor itself. So, suppose if E t, which is the RTD function, which is also called as the exit age distribution function, it is also called as the exit age distribution function, and let us define what is meant by age of, let us say, an atom or a molecule of a material. So, the age is given, it is defined as the time spent, that is the time that is spent by the atom or molecule in the reactor vessel. So, that is what is defined as the age of that particular atom or molecule of the material which is actually being considered. So, therefore, clearly E of t is essentially the age distribution of the effluent stream. So, age distribution as measured by the concentration of the species in the effluent stream, that is what is the RTD function E of t. So, now there are some definitions. So, we can now define what is this F t and E t. So, we need to define, in order to characterize the RTD function and in order to decipher some of the properties, we need to define some quantities, and the first one is F t. So, F t is essentially the fraction of the effluent which is actually resided for a time which is smaller than time t. So, F of t is basically fraction of effluent resided in the vessel for time less than t. So, now how is that defined? So, f of t, as we have seen in the step input case, is actually defined as integral between 0 to t E of t dt. So, that is the fraction of the effluent that has actually resided inside the vessel for a time which is less than t. Now, one can also define what is the fraction of the effluent which is actually what is the fraction of the material which is actually residing inside the reactor for a time which is longer than t. So, one can define fraction of material in reactor residing longer than time t. That is, what is that fraction of material which is actually staying inside the reactor for a time which is actually greater than t, and that is essentially given by 1 minus f of t, and that is equal to integral t to infinity E of t dt. So, sum of these two is obviously equal to 1. So, f of t, as mentioned earlier, is nothing but a cumulative distribution function, and such a definition was actually given by Professor P. V. Danckwerts. Danckwerts was the one who came up with this definition or this name for f of t, and this is basically area under the E curve. So, as we can read from the integral, it is the area under E curve, and and that is given by. So, if we sketch the f t versus time, so that will be, so the maximum possible value that f curve can take is exactly equal to 1. So, f t is essentially normalized, is a normalized, it is a normalized response to a particular input. So, f t is a normalized response to a particular input that is actually fed into the reactor. So, let us summarize what we have actually learnt in today's lecture. So, we have looked at what are the properties of the tracer which is required for it to actually function as a tracer to estimate the residence time distribution function. And then the two injection methods, which is the pulse input and the step input method, to actually decipher the residence time distribution function, and what are the different curves like the concentration curve and the E curve and the F curve, which basically characterizes the residence time distribution in the pulse and the step input method. And then we looked at what is this convolution integral which connects the concentration of the tracer to the input of the reactor and the concentration of the tracer as measured in the effluent stream. Thank you.